Welcome to Mrs. Neller's notes for her double block algebra class. These are the notes for section 7.5 entitled Special Types of Linear Systems. And today we're going to solve special types of systems of equations, meaning that they're going to have no solution or infinitely many solutions. And we're going to solve them by either graphing or doing substitution or elimination. And again, we're probably going to do substitution and elimination more, but graphing is a good way to look at it so that you can see what it means to have no solution or infinitely many solutions. So up until now, we have had linear systems that have one solution. So that means if you have your axes and then your lines, let's just say we have a line like that and a line like that. They cross at one point. So that's what we've seen so far. So your answer then is whatever that ordered pair is, whatever that XY ordered pair is for where the lines cross. That's your answer. Okay? So what would it look like if systems had no solution? So in order for them to have one solution, they have to cross. So if they're going to have no solution, that means that they wouldn't cross. So you would have lines that would be parallel. So that's one of our special cases that we're going to see today. We're going to have lines that are parallel. So that means that they don't cross. They have the same slope. Okay? So they do not cross, or they do not intersect, and then they have the same slope. Now the other special case that we're going to see is infinitely many solutions. Now the way that you can get one solution is for the lines to cross one time. But to get an infinite amount of solutions would be for you to graph the line and then graph the exact same line over top of it. So they are going to be the same line. So when you graph it, it looks like there's just one line. But what's really happening is that the lines are touching everywhere. They touch at every single point. And we abbreviate this by saying IMS, infinitely many solutions. Okay, so those are two special cases that we're going to see today. Now, you might still have some problems in your homework where you get one solution where the lines cross at a point, okay? But you're also going to see ones where they are parallel, so there's no solution, or where they're the same line, so then you can put IMS. Okay, so let's do a couple graphing problems. And remember, when we graph, we have to solve each equation for y first. So for part A here, I'm going to take this top equation. I'll do it in green. So we have negative x plus y equals 1, and I'm going to solve it for y. So I'm going to add the x over. So y equals x plus 1. And then the other equation, let me do that in red, is x minus y equals 1. So to solve that for y, I'm going to subtract the x. And then I'll divide everything by negative 1. So that's going to change all my signs. Okay, now notice that for my green line, my intercept is positive 1. And my slope is also a 1. So I'm going to go up 1 and over 1. Okay. And I can go down 1 and back 1 if I want to backtrack. Make some extra points there. And for my red line, my intercept is negative 1. But again, my slope is 1. So they have the same slope. So that means that these lines are never going to touch. They're parallel lines. So my solution is going to be no solution. Those lines will never cross each other. I will never get a solution. Okay, now for part B, we're going to do the same thing. I'm going to solve for y. So this first equation here, 2x minus 2y equals 4. I'm going to subtract the 2x over. So I'll have negative 2y, negative 2x plus 4. And I'm going to divide everything by negative 2. So y equals 1x minus 2. And then for the other line, let's do that in red. I'm going to solve it for y, so negative x plus y equals negative 2. So I'll add the x over. So y equals, x minus 2, or 1x minus 2. So right away, you should notice that these are going to be the same line. And students usually ask, do I have to graph it? Yes, you do. Okay. For these, if they give you a graph and they tell you to graph, you're going to graph. So I'm going to go to negative 2. I'm going to go up 1 and over 1. Okay, so I could go down 1 and back 1 too. So there's my purple line. Woo. And if I graphed the red one, I would start at negative 2 and I'd go up 1 and over 1, or down 1 and back 1. So it would be the same line right on top of the other one. Okay, so when that happens again, you have infinitely many solutions. So you can see, even when you do the work to algebraically solve the equations for y, you can see by the time you do that that you're going to have the same line. So it's going to be infinitely many. Or here for part A, you can see that they're going to have the same slope. So you know they're going to be parallel. So you know there's going to be no solution. But yes, you still have to graph the lines. We want to see those pictures of what's going on as well. Okay? Especially since the directions said to use the graphing method. That means you have to graph. Okay, now for example 2, we're going to try and use either substitution or elimination here to solve these systems. So we're going to see what a no solution or infinitely many solution process will look like algebraically. Now for part A here, I've got my x's and then my y's and then my numbers. So I've got both equations in standard form. Nothing is solved for x or for y. I don't have any x or y that's by itself. So I definitely need to do elimination here. And I've got my x's. If I want to eliminate them, I'll need a 14. My y's, if I want to eliminate them, I would also need a 14. So it doesn't really matter which one we pick. I'm just going to pick the top equation here, and let's eliminate the x's. So if I multiply that by 2, I'd have a negative 14. And on the bottom, if I multiply that by 7, I'd have a positive 14. So when I multiply everything in the top, I'll have negative 14x plus 14y equals 14. And then in the bottom, I'm going to have 14x minus 14y equals, negative 126. That's a big number. Don't be afraid of the big number, though. Now here, the cool thing that happens is that the x's eliminate and the y's eliminate. So that means I have nothing on the left side. I have 0. But I still have something on the right side. So when I add those, I get negative 112. But that's not true. 0 isn't equal to 112, or negative 112. So that's not a true statement. So this is no solution. So that means if I was to really graph these lines, they would be parallel lines. Okay? But that's what a no solution is going to look like algebraically. You'll have some statement that doesn't make sense. It may or may not always be a 0. You might have something like 5 equals negative 112. Okay, that's whatever it is, whatever the numbers are, they're not going to be equal to each other. That's what makes it a not solution, a no solution. Okay, for part B now. Now this one I could do substitution because this y here in the top equation is by itself. So I could solve the top equation for y and substitute it into the other. Or it'd be really easy to do elimination with this one too. If I multiplied this top equation by a negative 5, then I would have a 5y and a negative 5y that would eliminate. So again, this is personal preference. I'm going to do elimination just because I think it's easier to multiply 3 numbers than it is to solve the top equation for y and then substitute it into the other one and then distribute. It's a little less work if you're just doing the elimination. So my top equation then will be 15x minus 5y equals negative 20. My bottom equation, I didn't do anything to it. Oops, plus 5y equals 20. Oh, now what do you notice? These were multiples of each other. Okay, I have 15 and 15x. I have 5 and 5 for the y's. I have 20 and 20. And one is positive and one is negative for all of them. So that means I get 0 equals 0. Is that true? Does 0 equal 0? Yeah, that's a true statement. So this is what an infinitely many solutions algebraic answer is going to look like. You're going to have a statement that's true. 0 equals 0, or 5 equals 5, or negative 100 equals a negative 100. Doesn't matter what the numbers are, they're going to be equal to each other. Okay? So algebraically, if you get a statement that's not true, it's no solution. If you get a statement that is true, then it's infinitely many solutions. Okay, and we have one more here. This system, let's do substitution with this one, just because we want to keep practicing that skill. And because we have some variables that are by themselves, so I have an x and a y, I'm just going to solve this top equation for x though, and then I'll substitute it into the other equation. So if I solve that for x, I'm just going to add the y over, so x equals y. So that is this top equation. Okay. Now that's a pretty easy substitution. If I'm going to plug it into the other equation was 5x minus 2y equals 6. Now if I'm going to substitute, remember, I don't want the x anymore. I want to replace the x with what x is, and x is y. So now I have 5y minus 2y is 3y. And when I divide, I get 2. Hey, I got an answer. Oh my gosh. So here, this is kind of like what we've been doing in the previous sections where you're actually going to get an ordered pair for a solution. So now I'm going to take this and I'm going to substitute it back into my original equation. So I'll have x minus y equals 0. So x minus 2 equals 0. If I add the 2 over, x equals 2. So then my solution will be 2, 2. Now don't think that all of your ordered pairs for solutions are always going to have the same number. That's just coincidence that this is 2, 2. Okay? You could still have an ordered pair that doesn't have the same numbers. But this is just good review of the substitution method. You could still solve this part C with elimination. Okay? And we have 2 elimination examples up above, one where you're multiplying both equations by something and one where you're multiplying one equation by something. So again, this is really good review of all a variety of different methods here for substitution and elimination. So again, when you're doing the homework tonight, which is a worksheet, make sure that you're looking for those special cases, either graphically or algebraically, for no solution and infinitely many solutions. If you didn't pick up a worksheet in class, it is on the class website, so you can go there and print it off. And if you have any questions, come on in and see me before school.